There we go. Okay, welcome everybody to our latest webinar on the Southern Annular Mode and El Nino Southern Oscillation. So we'll start with the karakia actually. This is our SN's karakia.
Is it supposed to be silent, Justin?
Can you not hear that?
No.
So could you not hear that, Jim?
No.
Could anybody hear that?
No.
I could certainly hear it. Oh well, is it? Anybody want to say it for us? Jim, do you want to do that?
Oh, the pronunciation will be pretty bad, but I can if you like.
That would be wonderful, thank you.
Ke raro e te korawai kaitiaki, o te ketanui atane, ma te hau puhihi te pakahuakuhu. Ki o mata waka, te kahatane, tangaroa, manakitia, mai a tātou katoa. I roto i te hoku itianga, i te aorangi rau kaupapa, he te oranga o mātou, kia piki... Oh, apologies, my screen is just...
Hei te oranga o mātua kia piki ake I o rā Māori kia toi mātau e o rā mana hui e takie.
Okay. Yeah, apologies for that. I'm having mouse problems on this computer and it just flicked the screen off at a pretty bad time.
I thought I was being clever there with the recording, but that just didn't work either. So I'll cover really quickly what the ramp changes have been so we know what we're talking about. So SNs were contacted earlier on in the year about reviewing some standards, and they chose to review the level 3 standards for the externals in Earth and Space Science. And they took on most of our recommendations, but I think they messed up a little bit because they took out El Nino and La Nina from oceans, which are the ocean and the atmosphere process that we'll see from later on are intrinsically linked. So I think that leaves the ocean standard a little bit small. Other than that, they've just a few tweaks. They've removed tides and waves, which was always difficult to assess. And they put in nutrients, which I think has been in the standard and the exams. And more significant changes came from the atmosphere standard. So you can see there the stuff that's been removed in red, hopefully. So they removed aerosols from volcanic eruptions because I've seen exam questions on sea spray aerosols and other stuff as well, bushfires as well. And then they have removed the biological and physical pump, which are probably more related to oceans. And they removed that weather that's never really been assessed very well either. But the most significant change, I think, is that they put in the El Nino Southern Oscillation and the Southern Annular Mode into atmospheres. Which is a little bit different, but as I say, the ENSO is intrinsically linked to the ocean, and the Southern Annular Mode is probably as significant, even more so than the El Nino in terms of New Zealand climate. So we thought that was probably a pretty important one to put into the atmosphere as one. Okay, so what I'll do now is I'll stop sharing my screen and pass you over to James, who's kindly given up his time and come along to give us a talk on the new processes. Okay, I can see the share button. Where's the stop sharing?
Click it again or something.
There we go.
Or if I click share, will it override your...
Hopefully that might, yeah.
Let's try. Oh, yeah, there we go. Yes, yeah.
Cool.
Right. Now, where's my... Oh, there it goes. Hopefully everyone can now see my screen.
Yep, perfect.
Right, and I'll just get rid of some of the clutter on my laptop screen before I get going. Yeah, kia ora koutou, and thanks very much for the invitation to speak to you and sort of get a bit of access to the Earth and Space Science program in NCA, which I know is, for someone like me, is a pretty exciting development in the high school system. So it was interesting. Justin shared a number of the PowerPoints about some of the topics on the atmosphere and so on, and so it was really interesting to see what is being taught and what some of the thinking is. It's pretty cool. So as you've already heard, I'm speaking this evening on SAM and ENSO, Southern Annular Mode and the El Nino Southern Oscillation, and they're both pretty big topics. So I've got probably more slides than I really should have for this length of time, but I'll try and go through things reasonably quickly, all the same. So just to introduce what I'm talking about, Southern Annular Mode, the SAM, operates over the Southern Oceans. So it's very much a mid-latitude phenomenon. And it involves a feedback between the westerly winds that blow over the Southern Ocean, the Furious 50s and all that, and storm activity. So it's an atmosphere-only phenomenon. It doesn't really involve anything happening in the ocean, or it does talk to the ocean, you might say. Then the other end of the scale, the El Nino Southern Oscillation, the ENSO cycle, is in the tropical Pacific, and it involves a feedback between sea surface temperatures or upper ocean heat and the trade winds. So it's a coupled ocean atmosphere phenomenon, whereas the SAM is atmosphere only. ENSO, as probably everyone knows, is the biggest signal in the global climate system after the seasonal cycle, that is. And when I say the biggest signal, I'm meaning on an interannual, sort of seasonal to annual basis. That's a bit of a vague statement. If you look long enough back in time, you can find all sorts of strange things happening. But on that sort of human life scale, sort of a time scale, that's the biggest thing there is in the system. And it's based in the tropical Pacific, but its effects ripple across the world. Meanwhile, the SAM is the biggest signal in the southern hemisphere atmospheric circulation, and its effects affect the southern hemisphere weather in the mid-latitudes of the southern hemisphere. It doesn't really communicate with the rest of the globe, although you can find linkages, but they're pretty weak. And the SAM and the ENSO cycle are essentially independent of each other. They happen naturally, both of them, but there's no sort of overlap between the things that drive either of them. However, there is an interesting connection between the two over the summer months. I'll talk about this briefly at the end of the bit on the SAM. So to start off with information on the Southern Annular Mode, I'm going to start with just the sort of background average situation in the Southern Hemisphere, what the circulation looks like, and then talk about how the SAM is a variation on top of that. So here's one of my favourite pictures, plot of the annual mean winds at the pressure level of 1,000 hectopascals, which is essentially the surface of the Earth. The average surface pressure is 1,013 or so. So these are the winds very near the ocean surface across the Southern Hemisphere. And the most obvious feature of this plot is the big ring of westerly winds that blow around Antarctica, basically. I'll just, where are we here? I'll just change the pointer to the old laser pointer so I can wave that around. Hopefully you can see that. Anyway, south of New Zealand down to the Antarctic coast, you've got this ring, this permanent ring. It's there all year round of very strong westerly winds. This is at the surface of the Earth. And you can see the trade winds, the tropics and all the rest of it, but this ring of westerlies is the big deal in the Southern Hemisphere circulation. And it's there because of the north-south temperature difference, north-south temperature gradient. So you have a temperature gradient that implies a flow of air, and it implies a pressure gradient, and therefore winds. And the colours here represent the strength or activity in the storm track, that is, whereabouts there are storms over the Southern Ocean, or over the whole of the Southern Hemisphere, actually. And the darker colours are more storm activity, basically. And you can see that the storm track is exactly coincident with the strongest westerlies. So the most active storms are where the westerlies are strongest. So these are coincident, but it is no coincidence. They are both there for essentially the same reason, and that's this north-south temperature gradient business. So that's a plot of what's going on over the Southern Hemisphere, sort of looking down from above a two-dimensional XY latitude longitude kind of view. This next plot is a slice in the vertical, and this is what's known as a zonal mean plot. You see these a lot in the literature, in the textbooks. So zonal meaning along a latitude circle. So a zonal mean is averaged around all longitude. There is no variation in longitude in these plots. So what we've got on the bottom axis here is latitude from 90 south to 90, not north, to the equator. So it's the Southern Hemisphere only. And the vertical scale is height, kilometres on the right-hand side, and pressure, which is usually the unit used by researchers. It's just convenient on the left-hand side. So what you can see there, just to explain the contours, the black contour is the zero line. This is for westerly winds. The blue contours are negative westerlies, that is easterly wind. So you've got a light easterlies in the lower stratosphere in the tropics, but you've got this great big bullseye of red contours, positive westerlies, 5 metre per second intervals on these contours. So we've got 5, 10, 15, 20, 25, 30 metres per second in this jet stream. And the strongest winds are at the top of the troposphere. This is the thermal wind equation. I don't know if that gets talked about in the ESS program, but anyway, because we've got this big north-south temperature difference, we get westerly winds in between, and those westerlies become stronger as you go up through the troposphere. And it's only really at our latitudes between about 40 and 60 south that the red lines make it to the surface of the Earth. So we have, on average, permanent westerlies blowing across our latitudes, and they become stronger and broader in latitude as you go upwards. So the westerlies blow from about 20 south to 70 south or so at the top of the troposphere, but only in a pretty narrow band over the Southern Ocean at the surface of the Earth. Okay, so that's the average picture of what's going on in the Southern Hemisphere. And the reason we have this big westerly jet over the Southern Oceans, apart from the fact that we have the north-south temperature difference, it really comes down to geography. There's the two hemispheres looking down at each of the poles, southern on the left, northern on the right. And you can see the two hemispheres are almost mirror images of each other. Over the Southern Hemisphere, got this great big landmass right over the pole, and then pretty much no land at all between about 40 and 60 south. That's the two latitude lines there. Just ocean, so nothing to get in the way of the flow of the westerly winds. Meanwhile, in the Northern Hemisphere, that's just ocean at the pole, and you've got these whacking great continents in the mid-latitudes between, well, about 30 and 70 north, actually. So in the mid-latitudes, it's about 50-50 ocean and land. So that, and the big mountain ranges associated with these continents really block the flow of the westerlies. So typically, you actually have two westerly jet streams, two westerly flows, one over the Pacific Ocean and one over the Atlantic Ocean. So it's a different story in the Northern Hemisphere. You do see the same kinds of things, the physics is the same, but the geography really changes the detail. So in the Southern Hemisphere, it's all very simple, you might say, and sort of a natural laboratory, people often say. You can see these westerlies blowing really strongly, and they vary in a very coherent and I guess you would say obvious kind of way. So let's get on to actually talking about how they vary. So here's this plot again of the average westerly winds and where the storm tracks are. This is the average situation. And the SAM is just is a variation on this picture. So what happens with the positive SAM is the whole system contracts towards the pole. So the average latitude of the westerlies goes up, goes closer to, say, 70 south or 60 south, and the storms go with the westerlies. So the whole shooting match contracts towards the South Pole. And, you know, north of this big ring of westerlies and storms, you have the subtropical high pressure belt, essentially. You've got a ring of high pressures. So when the SAM is positive and the storms and the westerlies contract towards the pole, the big high pressure systems move southwards as well. And that's when New Zealand tends to have pretty fine weather. So for weather in New Zealand, this positive SAM is good news for us, unless of course you want some rain. You're an agriculturalist, perhaps. And then the opposite situation is the negative SAM, where everything expands out towards the equator. So the strongest westerlies move northwards up to more like 40 south, and the storms go with those westerlies. So in our latitude, you tend to get much wetter, stormier weather. So that's the negative SAM. Now, I was going to play a video from Agriculture Victoria, which is really nice. It's a couple of minutes. I'm thinking I won't play it now. We can have a look at it later on, maybe if there's time. But I'll just, in the interest of time, I'll keep moving. But the Ag Victoria people came up with some very nice little, quite amusing, but very informative little videos on how all these things work. So have a look at that later on, maybe. All right.
Can I just ask James real quick?
Yeah, sure.
There's a lot of Australian resources out there that I've seen, but the influence on New Zealand is pretty much the same as like Southern Australia, Tasmania, isn't it?
Yeah, that's a great question. And I've got in the notes pages, or notes for these pages, I've got a link to a NIWA website that is really good, and it's fairly recent. I just hadn't noticed it until fairly recently. It's got a lot of background on the SAM, and it has an up-to-date time series of what it's doing. And yeah, it talks about the effects on New Zealand. But yeah, the effects on Victoria and Tasmania are pretty similar to the effects on at least the South Island of New Zealand. It's very sort of constant latitude. So if you're at the same latitude around the other side of the hemisphere, you'd find the same thing. But you know, the thing is, there's very little land at these latitudes. There's New Zealand, the Southern Australia, and the Southern South America, and that's pretty much it, apart from a few islands. Yeah. But yeah, quite right. And of course, you know, as mentioned earlier, the negative SAM was a big player in the last few weeks. It's gone away now, but those huge windstorms that occurred 2 or 3 weeks ago were part of a negative SAM period. So yeah, when the SAM becomes negative, it's not always as vigorous as it was recently, but it can bring pretty stormy weather to most of New Zealand. So here's yeah.
So was that linked to the stratospheric warming then? So there's a link between the troposphere and the.
Yeah, great point. Yes. So the westerlies, the ring of westerlies blows around the pole in the stratosphere as well, and the stratospheric, the polar stratospheric jet in the winter is very, very strong. But it doesn't usually break down quickly in the southern hemisphere, but it has done a few times lately, and this is what happened back at the end of August and the beginning of September. That ring of westerlies in the stratosphere collapsed suddenly, and it's called a sudden stratospheric warming because the temperatures over Antarctica go up in the stratosphere very rapidly, 40-degree warming in 1 or 2 days kind of thing. So that destroys the north-south temperature gradient, which destroys the westerly flow. And if you slow down those westerlies in the stratosphere, that's going to slow down the westerlies right down to the surface of the Earth, and that pushes them towards the equator, a sort of conservation of annular momentum kind of story. So yeah, there was a collapse of the stratospheric circulation, and I think it was at the end of August or beginning of September. And it takes a few weeks for that to sort of circulate down to the surface of the Earth. But yeah, we had a period. We show you this is from this NIWA website. There's the URL. This is the daily time series of the SAM index. It's standard deviations. It's unitless, but positive values, positive SAM, negative values, negative SAM. And you can see from about sometime in August, we're into this negative period. And it's not the strongest negative by any means. Even back about this time last year, there was a big downward spike. It didn't last very long. And if you look back through the time series, through the data we've got back for the last 60 or more years, there are periods that were considerably more negative than we've seen lately. So it can be extremely strong, the anomalies in the weather locally sometimes. And, this is all painted as a sort of ring around Antarctica and everything varies in the same way at all longitudes. The reality is that it doesn't actually do that. There are regional differences sometimes. So we just happen to cop an extreme strong bit of the westerly jet over New Zealand in the last few weeks. You wouldn't normally expect it to be that stormy with this kind of -1, -2 SAM index. We were just, you could say, we're a bit lucky maybe. Anyway, have a look at this website. It's updated daily or every few days, I think. And it has all the statistics about what the SAM's doing, how many days of positive and negative SAM there's been this year, all that jazz. So it's got some really nice background information. Okay, so you can see that this plot, it's very noisy, there's lots of ups and downs. But there's a sort of natural timescale here. It stays negative or it stays positive for a week or two. That's the kind of typical timescale. It can change from positive to negative very quickly over the matter of a day or two, but it will stay in one state or the other for a couple of weeks, typically, once it gets into that state. So what's driving all this? The feedback that drives the SAM. Why does it vary the way that it does? And there's lots of nice papers published on this, and I could show lots of equations and talk about physics. I've attempted to write it down in English in the way that I understand it. Hopefully it makes sense to all of you. So, like I said before, the westerlies and the storms are strongest where the north-south temperature gradients are the strongest over the Southern Ocean. And this is, at the same latitudes. So both of these features are over the top of each other or mixed in with each other. And storms, when they develop, they take energy from this background temperature gradient. That's what gives them the energy to develop the winds, the kinetic energy, and so on. And that sucks a bit of energy from the background flow, from the average westerlies. So they take a bit of energy away from this background state. But then as they move away, they're going to drift away north or south. Just the dynamics of how they work. They actually send momentum or energy back from where they came, back in the direction they've come from. So storms developing and then moving away, there's a flux of energy back to the latitude of where they started. So they actually help to maintain the westerly jet by forming and moving away from the latitude of the jet. So the temperature gradient and the westerly jet are both helped along by the action of these storms. So there's quite an intimate connection between the storm life cycles and the location and strength of the average westerlies. So if storms for some reason started forming at a different latitude regionally, over the southern Indian Ocean or something going on, and we started to get storms forming further north than they had been, they can basically drag the westerlies with them because of this feedback process. And everything's zipping around the hemisphere pretty fast, so this can translate quite quickly around the hemisphere. So typically what happens is storminess moves north or south, and that drags the westerlies. It takes a little while, but over the course of a week or so, it can move the average westerlies. And that gets translated around the whole hemisphere quite effectively by the background flow. So when you look on, say, a monthly average basis, or even a weekly average, the net result of all this is a sort of a north-south pulsing, or concertinaing, if you like, in the average latitude of this whole system of storms and the westerly jet. It's all happening locally, over particular ocean basins, at particular latitudes and so on. But it just, the way it all works, it gets communicated quite quickly around the whole hemisphere. Well, another way to put all this is to say that You know, the westerlies and the storm really are energy sources for each other. They talk to each other. If one moves in latitude, the other follows. I mean, I suppose you could move the westerlies somehow and the storms would follow, but usually, in fact, almost always, it's the other way around. Some storms move and the whole system follows. And the strength of this coupling between the storms and the westerlies, which, you know, there's no sort of physical rule, that's how strong that coupling is. And there's been some interesting modelling studies looking at changing that in, you know, toy models. You can make the SAM behave really ponderously or can go away completely if you do away with the coupling. But the sort of typical strength of the coupling, that's what dictates timescale of variability of a matter of a few days to 2 or 3 weeks. Yeah. All right. So hopefully that was all crystal clear. And really, you know, I've had a few questions. Happy to take questions as we go. We can talk about it later on. So just to get back to the sort of consequences of all this, just show some plots of sort of average changes in the weather at the surface associated with the positive and negative SAM. And so on the top left, I've got this average state of the westerlies and the storminess, and these, I don't know if this is a real word, concertina and westerlies. So in the positive SAM plus on the left, these are just averages over about 1,000 days, and it's taken during the summer, November to February, because that's when the SAM is most annular, most circular. It's there all year round, but other things get into the mix in the winter, and let's not talk about those. It just complicates the story for no particular reason. So, okay, so the colours here, the orangey colours are the same as the ones in the average plot. So where the colour's darkest, you've got the most storms. And the blue colours are the opposite. The darker blue are where you've got the least storms. You've got less storms than normal. And the arrows are the wind circulation difference from normal. So arrows that are pointing towards the west, easterlies, doesn't mean the wind's actually easterly. It's just the westerlies are weaker. So in the positive SAM, we've got this ring of storminess, increased storminess at about 60 south or maybe slightly south of that, and stronger than normal westerlies. And at the same time, at about 40 south, we've got a ring of less storms than normal and winds, weaker westerly winds, different from normal from the east. So you'll notice that New Zealand sits underneath this darkest patch of the blue. So New Zealand is the country in the middle latitudes that feels the positive SAM most strongly. We have a lot less storms happening. The winds are lighter, the sun comes out, the weather's generally settled during the positive SAM over New Zealand, especially in summer. On the other side of the plot here, the SAM minus, SAM negative, again for about 1,000 days. And you can see it's not quite a mirror image, but it's pretty close. In the negative SAM, you've got a lot less storms around the Southern Ocean at 60 south, and you can't even see the wind arrows, but they're all pointing towards the west. They're all easterly differences from normal. So the westerlies are a lot weaker than normal over the Southern Ocean in the negative SAM. And all of that energy moves northwards, and it moves, again, New Zealand is pretty much under the darkest patch here. That gets the biggest increase in storminess in the negative SAM, and the westerlies pick up noticeably, as we saw a couple of weeks ago over New Zealand. And it's not a continuous ring. You know, there are regional variations because of the topography and all the rest of it, but broadly speaking, we see a pretty symmetric change between more storms near Antarctica in the positive SAM and more storms in the mid-latitudes in the negative SAM. So that has obvious consequences for the surface weather over New Zealand, which I'll show a little bit more about in a minute. So these plots are from actually that last one here. That's something I drew. I must write a paper about it. It's not published, but these plots they're from a paper by Dave Thompson and co-authors, published a wee while ago now, 15 years ago. This is for the positive southern annual mode, again in the summer, December, January, February, and these are essentially averages for a +1 standard deviation positive SAM. So what we see on the left here is the average difference from normal in the westerly winds. You see the westerlies, and New Zealand only just appears at the edge of this plot, so this is all south of 50 South. The westerlies are stronger around Antarctica. The blue colours indicate temperature differences from normal. So over Antarctica, it tends to be colder during the positive SAM. And the idea there is that the winds, the circulation of the winds and the storms are kind of isolating the air over Antarctica, so it can cool down more. And if you've got stronger westerlies, you're going to have a bigger north-south temperature gradient. So you have to have colder conditions really over the Antarctic continent to be consistent with the way the winds are changing. The exception to that rule is the very northern tip of the Antarctic Peninsula, which actually sees higher temperatures, as you do see in southern South America. And this is by and large the effect of foehn winds, northwesterly winds flowing over the mountains, just as they do in Canterbury and eastern New Zealand. And you see warmer conditions when the westerlies pick up there. Okay, and on the right, got the wind plot again, but now we've gone right out to 20 South, I think it is. You can just see New Zealand in here, and you can see the ring of westerlies near Antarctica, but then sort of relative to normal easterlies at our latitudes. And the colours are sea surface temperatures, how they vary with the SAM. So you have a ring of colder sea temperatures at the ocean at the surface at higher latitudes, and then broadly speaking, between about 20 and 40 South or so, you tend to have warmer sea temperatures. And this pattern here is actually reminiscent of what you might see in a La Nina state, and I'll get onto that later on. So there's a connection to the ENSO cycle in terms of the way sea temperatures vary. But broadly speaking, it's doing its own thing, usually. Okay, so that's temperatures and winds. Precipitation, this is another plot I drew. It's a bit garish based on a global rainfall data set, but just doing correlation between the SAM index and gridded rainfall anomalies monthly over the southern hemisphere. So I haven't got a colour scale here, but the orangey plots are drier conditions and the bluer plots are wetter conditions, and the sort of greeny yellow is not much change. I probably should have blanked that out. So this is for the positive SAM again. We see this ring of dry conditions between about 40 and 50 South or 55 South. And then closer to the Antarctic coast where the storms have moved, we see wetter conditions. So average rainfalls are affected again across the whole of the southern hemisphere really. And if you go to lower latitudes again, across a good part of southern Australia, it's actually wetter in the positive SAM, and that's because some of the tropical rainfall systems that are blocked off by the high pressure belt in the mid latitudes. It's in the subtropics because that moves southwards. That lets these rain-bearing systems in to eastern Australia especially. But for New Zealand, their positive SAM you can see is broadly speaking drier, and it's also warmer because it tends to be more settled and sunnier and so on. And going back to that Thompson et al. Paper, that's captured in these plots here. So again, December, January, February, positive SAM conditions. The arrows are the difference from normal in the winds, so easterlies, that means weaker westerlies. And the temperature plot here in degrees C, you can see most of the countries, all of the countries on the positive side, or yellow or brownie. So New Zealand is warmer overall in the positive SAM, but not really much up the east coast of the North Island and in Marlborough. And that's because when the westerlies are blowing, you get these foehn winds, the downslope winds, the warming that comes from the orography, the mountains. So you have less of that during the positive SAM. It tends to not warm up much in those regions, but especially on the west of the South Island, it's the opposite story. You have less of the westerlies booming in and bringing rain and cloud and so on. So it tends to be sunnier and warmer in western regions. On the right-hand side, the rainfall difference from normal, same story. The westerlies are weaker, so it tends to become a bit wetter in the east and drier, noticeably drier, especially on the west coast of the South Island and in Southland. And this is the same deal, the westerlies are weaker, so you've got less storms coming into the west coast and rainfalls go away to not a large extent. There's a lot of rain falls on the west coast, even in the positive SAM, but it is generally drier right through the west of New Zealand, right up to the Auckland region, roughly speaking. So that's the effects on New Zealand's weather and climate, and you see the similar things for Tasmania and for parts of Victoria, but Australia's far enough north of New Zealand that the rules change a bit with the SAM thing. It's quite specific on what latitude you're at as to what the effects are. Okay, last thing I was really going to talk about, and one of the last things, was this connection between ENSO and the SAM, and I'm showing you this complicated looking plot from this paper by LaRue and Thompson, and I don't think I put the link to that in the notes, but I can send it through. This plot is regression coefficients on the inverted cold tone index. So a lot of jargon for taking sea temperatures in the tropical eastern Pacific and looking at the time series of those and correlating or regressing them on the strength of the westerly winds at each latitude. This is again a zonal mean thing, so you average the westerlies around the globe, got a time series of those at each latitude, correlate it with this sea temperature time series from the tropical Pacific. So we've got latitude from the North Pole to the South Pole here, and time from July through to June. So the southern summer's in the middle here. And you can see this region here where you've got quite a lot of solid contours. That's positive correlations, positive regression coefficients. And the shading is where these numbers are significant. So you've got this big bullseye here, centered on November, December, but it covers the summer months basically. Centered at about 60 south, where you've got this positive relationship between this particular time series. The way it works out is it means that in a La Nina event, you have stronger westerlies over the Southern Oceans, and in an El Nino event, you have weaker westerlies over the Southern Ocean at 60 south. So this is one of the first papers that showed that a positive SAM goes with a La Nina and a negative SAM goes with an El Nino, but only between November and February. Nothing happens in the winter. And there's been, I wouldn't say it's that well understood even now. This is, 10 years ago, 20 years ago, sorry now. There's been quite a bit of work done on this, but it's not obvious really the physical mechanism behind it. There are some good explanations. I'm not going to go into that. But just to go into a bit more detail of what's going on, you can plot a spatial map, latitude, longitude. Again, you do regressions or correlations using this temperature index from the tropical Pacific, and on the pressure field, let's say, and you get the positive values are solid lines and negative values are dashed lines, and you see this region of low or negative correlations over Antarctica and positive correlations in the mid-latitudes. You can think of these as like pressure contours, if you like. So you've got much lower pressures over Antarctica, higher pressures in the mid-latitudes. This is very like the pressure pattern you see in the positive SAM. So it makes a consistent story from a statistical point of view as to why this is going on. It has remained slightly mysterious. I think one of the best papers talking about this was this one by Ding and co-authors that came out, over 10 years ago now, talking about, this is just a schematic. So you've got the subtropical jet to the north of New Zealand, the jet associated with the SAM sitting over the Southern Ocean. And in an El Nino event or a La Nina event, these lines here represent Rossby waves, these big scale wave patterns that propagate out of the tropics associated with an El Nino or a La Nina event. They're ways for the tropical atmosphere to shed energy, basically. And the typical thing across the Pacific is that one of these wave patterns starts in the region of the subtropical jet over Australia, and you get this sort of low, high, low, high, low wave packet that propagates through the South Pacific and into the Southern Indian Ocean. Southern Atlantic, sorry. And just going back to this previous plot, you can see this big region here of negative values. This is associated with the Armonts and sea low, which is a sort of permanent feature of the circulation near the Antarctic coast. You've got a sort of a high near New Zealand, a low here, low up here. It sort of maps onto this wave packet story. And the idea basically is that these Rossby waves form in an El Nino or a La Nina event, and they project onto the pressure pattern associated with the SAM, so they can trigger it to go from positive to negative and back again, kind of thing. So that's one of the mechanisms. And then there's something else happening over the Indian Ocean, which is a slightly different story. I won't bother going into the details again. I don't think I put the link to the paper in the notes. I can send that through afterwards. But yeah, that's to me the most plausible story I've heard about this, that you've got these waves that come out of the tropics and they just sort of project onto the SAM pattern and push it around. Okay, last thing I want to talk about with the SAM is the trends in what's going on with the overall SAM pattern. So we've got the average picture of the westerlies and the storms, and on the right is a time series of seasonal averages of the SAM index. And you can see again, it's very noisy, lots of ups and downs. But the black line is I think it's like an 11-year smoothing on top of all this, and you can see that line does go up. And actually it's statistically significantly upwards on top of a huge amount of noise. So it's only just significant. And really, what we're not talking about the average SAM index going from minus 0.5 over here to plus 0.5 there. It's more about the chances of getting a positive SAM season or a month versus the chances of getting a negative SAM season. So back in the 1960s, you're much more likely to have the negative SAM happening. In the 2010s, you're much more likely to have the positive SAM happening, and that's a good way to think about it. We're just more disposed to having the positive SAM in the last couple of decades. And what's going on there is the westerlies themselves, the circulation of the westerlies is getting stronger. And again, from a sort of conservation of momentum point of view, angular momentum, you have to move towards the axis of rotation, so the whole thing contracts on the pole. So the reason that we're getting a stronger westerly flow is we've got a stronger north-south temperature difference. And there's two things going on there. First of all, global warming. We're adding greenhouse gases to the atmosphere, and this is the pattern of warming over the globe. This is the last full 10-year period, 2015 to 2024, minus a sort of standard reference period, 1951 to 1980. The global average change here is 1 degree, basically. But for the southern hemisphere, you can see, and this is from the NASA website, I think I put the URL in the notes. You can see over the Southern Ocean, there's almost no change in most places. Yes, there's some warming over the peninsula, etc. But when you average around the globe, the change in temperatures over the Southern Ocean latitudes is pretty close to zero. Meanwhile, in the tropics, things have been warming up at about, close to the global average rate, between 0.5 and 1 degree. So the north-south temperature difference in the southern hemisphere has increased. The opposite's happening in the northern hemisphere, by the way. The Arctic's warming up extremely rapidly. So we're seeing a decrease in the westerlies there, and this sort of more wavy jet stream and polar outbreaks and all that jazz. But in the southern hemisphere, we're seeing an increase in the strength of the westerlies because of the way climate change is playing out, basically. But that's one effect. The most important effect has actually been the ozone hole. And this was a plot from NASA, I think it was 2006. Ozone hole, and these colours represent the amount of ozone in the air column everywhere in the southern hemisphere. So the purpley colours are where you've got very low ozone. So you've got this hole, not quite, it doesn't go away completely, but you've got this relative hole in the ozone layer, roughly centred over the pole. And then you've got, plenty of ozone in the mid-latitudes, and New Zealand is just here somewhere, is it? Anyway, over New Zealand, we haven't lost ozone, although people like to say we have. That's really at high latitudes. And the issue here is that ozone is one of the few gases in the atmosphere that absorbs sunlight directly, especially ultraviolet. That protects us from all the UV. So if you take ozone away, you're going to have less heating of the atmosphere by absorption of sunlight. So the air is going to cool down. So where you've got the low ozone region, you've got colder conditions. So again, you're going to increase the north-south temperature difference because you've cooled high latitudes down, but you haven't cooled down a lower latitude. So the ozone hole increases the temperature gradient in the lower stratosphere. And this gets back to the story about the stratospheric westerlies and so on. So what happens in the stratosphere affects what happens at the surface of the Earth a month or two later, basically. So, so yeah, there's these two effects: the ozone depletion, which has been going on for 50 or 60 years or so, and the way greenhouse gas increase is changing the distribution of temperature changes. In the past, both of these things have worked together. They both increased the north-south temperature difference. But in the future, or from about here on, they're going to work against each other because the ozone hole is starting to repair itself. It's got quite a long way to go, but the idea is over the next 50 years, this hole will fill in, which would drive a decreased north-south temperature difference, so a negative SAM trend. Meanwhile, if we don't get on top of emissions of greenhouse gases, that still drive a positive trend. So maybe they're going to cancel out. Who knows? We'll have to see what happens with greenhouse gas emissions reductions, what people decide at the COP meeting this week and so on. So yeah, so it's a bit of a complex story, but basically, if you increase the temperature difference from the equator to the pole, you increase the strength of the westerlies, and those westerlies move southwards, so you get a positive SAM influence. Okay, I might just stop there for a minute or two. And what time is it? 7:45. Gee. If there are any other questions, the rest of my material's on the ENSO cycle, which is a different topic altogether. So anybody have any questions on this stuff so far?
It's not directly related, I don't think, but the stronger westerlies as they get closer to Antarctica, is that going to affect the sea ice and the land ice?
That's a great question. The answer is yes, and it's a very active research topic and something that I'm personally involved in. But yeah, the way the SAM has varied has definitely affected Antarctic sea ice, both sort of hemispherically, but also regionally, because there are, it's not just westerlies. You get a few kinks. So you get sort of flow more from the north near the Antarctic Peninsula that can cause sea ice loss, flow more from the south over the Ross Sea that can produce sea ice gain, and so on. So yes, the short answer is yes. And exactly, again, the mechanisms of how that all fits together are still a topic of research. And then we don't know what the SAM is going to do in the future. It depends on greenhouse gas emissions. So how the SAM is going to affect sea ice and therefore the ice shelves and land ice and temperatures over Antarctica is, a bit of an open question at the moment, a bit of a worry that we don't really know how the SAM is likely to play out over the rest of the century, basically.
Thank you.
Oh.
I had read somewhere that the expansion of the Hadley cell sort of southwards and northwards with extra heating kind of around the equator and that sort of stuff also had the effect of enhancing, was preventing the mending of the ozone hole or the thickening of the ozone layer.
Right.
Because that was kind of pushing that SAM thing south. Is that right?
Yep. Yeah, that's another great question, Jenny, and a great observation. And yeah, I'm thinking there's a lot of things I'm not saying. I'm saying plenty, but there's plenty I'm not saying as well. Yes, so the Hadley cells in the tropics are gradually getting wider as the atmosphere warms up, and you could think of the Earth as just gradually getting a bit more tropical. So the tropical circulation is expanding a bit, and the mid-latitude circulation has to sort of move out of the way. So part of the story also is that as the Hadley cell expands, you'll naturally get a contribution to the positive SAM trend. The storms and the westerlies just have to move to high latitude. And it's not a big effect. We're only talking a degree or two of latitude, but it's there. It's measurable. It makes sense from a theoretical point of view. And then there's a whole lot of arguments in the literature about, is it the Hadley cell, is it the tropical circulation that's pushing the westerlies and the SAM towards the pole, or is it actually that's happening because of ozone depletion and all that, and that's pulling the Hadley cell southwards? Because, everything's connected, right? And the storms are playing a crucial role, getting energy out of the tropics and all the rest of it. So if one moves, the other has to again. So it's, in my mind, that's not a particularly interesting question. Who actually cares what's doing the driving there? But they are related to each other, certainly. So yeah, that's a good point. Yeah. Right, or maybe I should move on to the ENSO stuff, or I will be here till midnight. So I'll just shift that little box. Okay, so where we were, this is the last SAM slide. So let's move on to the ENSO story, which is quite a change of gears. It's in the tropics, and it's a totally different story in a lot of ways. So starting off with the distribution of sea temperatures. So it's this material, ENSO used to be covered in the oceanographic part of the Earth and Space Science curriculum. Now it's in the atmosphere part. And, there's no one home for this stuff because it's very much a coupled phenomenon, but the ocean surface or the upper ocean is intimately connected in all of this. So anyway, here's a plot of ocean temperatures, an annual average, and as I often do, I've got no colour scale to tell you what's going on here. So this second to darkest brownie colour here, that's the 28-degree isotherm. So all of this region, the surface of the ocean is 28 degrees or more, and the darker bit here is 30 degrees. So it's a 2-degree change for every change in the colour scale. So this is the Western Pacific warm pool over here. This is the warmest place on the planet in terms of the total amount of heat in the ocean. And New Zealand sits directly south of us, so does Australia. And the Hadley cell is actually strongest in both hemispheres in this region, because this is where the north-south temperature difference is greatest. You've got the warmest seas here, and it's sort of uniformly cold at high latitudes, but you've got the biggest north-south gradient between about 100 east and the date line, roughly speaking. So you see this Hadley circulation very clearly in our part of the world. Anyway, we've got this warm patch, or the warm pool, over in the Western Pacific, and then along the equator near the South American coast, it's actually a bit hard to see with this colour scale, but sea temperatures at the equator in the Eastern Pacific are about 8 degrees cooler than they are in the Western Pacific. So it's quite a curious thing. Right along the equator, where the solar intensity is greatest, you actually got this pretty significant east-west temperature difference. Now, part of the story is the Humboldt current that comes up the west coast of South America and brings cold water northwards, and that flows westwards under the trade winds, which blow from east to west in the tropics off the coast of South America. But there's a little bit more to it than that. As the winds push the water towards the west, the change in the sign of the Coriolis force, basically the way the rotation of the Earth affects motions on the planet, the water that's flowing westwards from South America is going to want to move towards the pole in both hemispheres. So it's going to move north in the northern hemisphere and south in the southern hemisphere. So the water diverges at the surface of the Earth. And so you have to have upwelling to avoid a vacuum forming, I suppose. So you get colder water from depth coming up to the surface along the equator in the Eastern Pacific. And that's the other contributor to this cold tongue, so-called. So you've got this colder water in the Eastern Pacific centered on the equator. and then the warmer water, the warm pool over in the Western Pacific. So this difference in temperature produces a difference in pressure. Where the water's warmest, where the temperatures are highest, you're going to have lower pressures at the surface of the Earth, upward motion, rainfall, all the rest of it. In the cooler region, you'll have higher pressures, downward motion in the atmosphere, and lower temperatures, etc. So you've got a relative high over in the Eastern Pacific and a relative low in the Western Pacific. That's going to drive winds to blow from east towards the west. So this temperature difference drives stronger trade winds. Now the winds are blowing from the east right around the hemisphere in the tropics, but they are stronger across the Pacific, noticeably stronger because of this temperature gradient. So the average state shown in the sea temperatures here goes along with an average speed of trade winds. And you could say this is an equilibrium state, but it's an unstable equilibrium. This is how the whole ENSO cycle works. If you can tweak one of these, if you can change the temperature gradient somehow, that'll change the strength of the winds, which will feed back and change the temperature gradient further. And you can either wind it up into a La Nina or sort of wind it down, if you like, into an El Nino event. So it's a really interesting phenomenon. It's sort of sitting on a knife edge a lot of the time. And the knife edge becomes most apparent about April, May, sort of the end of the autumn, southern autumn. And over the southern winter, the whole system decides what it's going to do. Is it going to ramp up into an El Nino or a La Nina? And in quite an unpredictable kind of way. Okay, so what's the feedback that's going on here? I've already described it, I guess. The east-west sea temperature difference affects the east-west surface pressure difference, which affects the strength of the trade winds. And the strength of the trade winds affects the sea surface temperature difference across the tropical Pacific. So these two things, the atmosphere and the ocean, talk to each other pretty strongly. Well, I should say, the atmosphere doesn't always listen to the ocean and vice versa. Sometimes you get an increase in the east-west temperature gradient, which we have at the moment, and the atmosphere doesn't respond by increasing the strength of the trade winds. So we've got a sort of a La Nina state at the moment, but the atmosphere is not too convinced. And that can go the other way as well. The trade winds can change their strength, and for some unknown reason, the ocean temperatures don't really adjust. Something else is going on. So there's a few mysteries still around the ENSO cycle, even though it's been studied very extensively for the last 50 years or so. So let's have a look at some sort of schematics of what's going on with the different states. Starting off with the sort of neutral state, the average, as I showed before, with the sea temperatures and so on. So looking in a bit more detail, here's the tropical Pacific. We've got cooler water over near South America, warmer water near Indonesia, and the trade winds are blowing from east towards the west. And the overall atmospheric circulation is known as the Walker circulation. So the air flows towards the west, gets to the warm place, you've got upward motion, formation of clouds and rain, and then that air flows back towards the east at the top of the troposphere, cools down and sinks into the cooler, higher pressure region at the surface of the Earth. So this overall overturning circulation is known as the Walker circulation, after Gilbert Walker, the person who first noticed what was going on in the atmosphere across the tropical Pacific 100 or so years ago. In the ocean, in the upper ocean, we have this situation here, this white bar labelled equatorial thermocline. That's the boundary between what's called the mixed layer, the upper part of the ocean that has pretty similar temperatures with depth. And then underneath that, you've got the deeper ocean, which is a lot colder and is operating on a totally different sort of paradigm to the mixed layer. And we have upwelling in the east from the deeper, colder ocean up into the surface waters associated with the Humboldt current and with this business with the Coriolis force and the divergence at the equator. Right, so in the neutral conditions situation, average kind of situation, we have quite a deep mixed layer in the west, and it's pretty warm, so you've got a lot of heat, not just at the surface, but down to maybe 200 meters or so. In the east, it's cooler and this thermocline is much closer to the surface, so you've got quite a shallow mixed layer in the eastern Pacific. And the trade winds are helping to maintain all of this as well as the surface temperature gradient. Okay, so what happens when things break down in an El Nino? What's going on is that the water circulation breaks up, really. So these arrows are representing differences from normal. So instead of upward motion over the Western Pacific, we now have relative downward motion. And the warmest waters have moved into the Central and Eastern Pacific. And the rainfall and convection basically follows that. So the region of strongest convection moves into the Central Pacific, and you get this like reverse Walker circulation over the Western Pacific. And the what you might call the real Walker circulation, if you like, the normal Walker circulation, contracts towards the east. So things get quite complicated in the atmosphere in an El Nino in a sense. And as the trade winds are weakening and possibly even reversing in direction sometimes in the Western Pacific, that warm water in the west gets to move eastwards. Or you could say that the water gets to move eastward and that causes the change in the Walker circulation. Again, that's, chicken and egg kind of story. But basically the thermocline flattens out and a lot of warm water gets to move eastwards. And it's transported by Kelvin waves that propagate along the thermocline. It's really interesting physics, but again, I'm not going to go into the details. But if you want to read about it, there's many places you can look this up. And I've given a couple of websites, I think, in the notes. So you get a lot more warming through the top 100, 150 meters in the Eastern Pacific, and quite a bit of cooling in the mixed layer in the Western Pacific. The net result is this east-west temperature gradient decreases a lot. It can actually completely vanish in a strong El Nino. And the strongest convection, the upward motion and rainfall, normally is in the west, moves into the Central Pacific, typically between about the date line 180 degrees and about 140 west kind of thing. And the crucial thing here is that where you've got convection and cloud formation and rainfall is where you're heating the atmosphere, because it takes energy to evaporate the water vapor in the first place. This is the so-called latent heat associated with water vapor. Where it condenses back into water, you release that heat. So you're warming the atmosphere here, and it's warmer than it would normally be. So it has to, radiate that energy away to get back to normal, as it were. So this is where these big, large-scale wave patterns, like the schematic I showed before, come from. It's the atmosphere shedding energy, and it radiates the energy almost completely over the globe, certainly across the North and South Pacific basins. And I've got down here positive feedback carries its own demise. And what I mean there is when you decrease the trade winds, that decreases the upwelling here, and it decreases the pushing of the warm water westwards over here. So it decreases the temperature gradient. And decrease the temperature gradient, that's going to decrease the strength of the trade wind. So it's that positive feedback. But you can see the diagram at the bottom here, these waves that travel on the thermocline carry heat towards the east, and it takes a few months to get from here to here in the ocean. But following behind the warm pulse, there's a cold pulse. So these waves eventually carry colder water towards the east. So this is this idea of its own demise. It sort of shuts itself down, and the timescale for that is how long it takes the warm water to get to South America, and then how long it takes the cold water after that to make it to the South American coast. And the whole cycle takes about 9 or 10 months. It's most susceptible to start doing something about the middle of the year, and typically one of these events lasts until about March or April of the following year, and that's all to do with the timescale of how fast the heating and cooling moves across the tropical Pacific in the ocean. Right. Oh yeah, and then a La Nina state is the opposite of an El Nino, and La Nina is like sort of like a super version of normal. You've got cooler water in the east, warmer water in the west, trade winds, but the trade winds become stronger than normal, the temperature gradient becomes stronger than normal, and the whole Walker circulation ramps up. So you get more rainfall than normal in the place where it's normally wet anyway, and less rainfall over in the east where it's normally cold. And the thermocline, you can see on the diagram at the bottom, the slope on that increases. It comes almost to the surface over in the Eastern Pacific, and it gets pushed downwards in the west. So you get a big disparity in the amount of heat in the ocean between the west and the Eastern Pacific. In a La Nina, it's the same deal. It's a feedback process. You increase the trade winds, that increases the temperature difference, which increases the trade winds, etc., etc. But again, it's got this own demise idea. You carry cold water eastwards, but a pulse of warm water is going to follow behind a few months later, so it will shut itself down within a year or so. Having said that, sometimes it doesn't. There are cases where we had 2 El Niños or 2 La Niñas in a row. So this sort of cartoon of what goes on is not the full story. You know, there are wrinkles on all of these, like everything to do with the real world, I suppose. Right, I better press on. What time is it? It's already 8 o'clock. Yeah. All right, so looking in the atmosphere, what's going on with this southern oscillation, which is the ESO part of ENSO? El Nino is more a description of what happens in the ocean. Southern oscillation, what happens in the atmosphere. And the history of this is interesting. You know, the El Nino was named by fishermen who live on the Peruvian coast, who noticed every few years the anchovy fishery just went away. And this was an El Nino event where the sea temperatures go up here. And Gilbert Walker, who was working in the Raj in India in the 1920s, started doing some correlation analyses and found that there was this east-west seesaw in surface pressures over the Pacific, which he called the Southern Oscillation. And it took many decades before people realized that these two things were connected with each other. But anyway, this graphic here shows these are correlation coefficients. So the red lines are positive correlations, the blue lines are negative correlations. Contour interval here is 0.1, I think. So we've got about a plus 0.7 over here and a minus 0.6 over here, roughly speaking. And what this correlation business is all about is with the Southern Oscillation Index. And the Southern Oscillation Index, the SOI, is just really the difference in temperature between Darwin in Australia and Tahiti in French Polynesia. And that's just because when Walker was doing his original analysis, 100 years ago, these were two stations that already existed that had reasonably long time series of pressure. So they were convenient for him. It turns out they are close to the poles of this ENSO cycle conveniently. So it's still used. This east-west difference between Tahiti and Darwin is still the standard SOI. And there's a bit of normalization goes on, but that's basically the story. You just take the difference in pressures here and you correlate that difference over the whole globe. And you see it's almost a global phenomenon. Everything west of about the date line across to Africa, pressures go down in the positive SOI, that's a La Nina. And everything from the date line across to South America, the pressures go up. So the east-west pressure gradient increases, so the trade winds increase in a La Nina. And you just change the colours for an El Nino, pressures go up over Australia, and they go down in the Eastern Pacific. And the pressure gradient decreases, and you get relative westerly flow. And you can see that the black line is a zero correlation line. It lies right through New Zealand. So the average effect on pressures over New Zealand is nothing. But the winds blow along the isobars, and the winds will even blow along correlation lines, if you think about it. So when you have lower than normal pressures here, you've got flow from the northeast. In a La Nina, we tend to get more winds from the north and northeast, warmer conditions and so on. In an El Nino, you've got higher pressures here and winds coming in from the southwest, and it tends to be cooler and stormier, etc. So this map tells us something about how the weather over a place like New Zealand is affected, even though the correlation with the SOI is basically zero everywhere. And this SOI quantity is very strongly related to the sea temperatures along the equator in the Eastern Pacific. So let's just have a quick look at that. Here's time series, and this is from the NOAA website. And I think I've had a look at these websites recently, even with the shutdown in the US. I think they're all still operating. kind of, but that sounds like the government's coming back to life over there soon. So the SOI at the top here from 1950 to fairly recently, it's bouncing up and down. You can see the timescale here is much longer than for the SAM. These are years, so you have years or even 2 or 3 years in a row where you've got positive SOI, La Nina, or negative SOI, El Nino. So it's much slower variability because it involves the ocean. Anyway, that's the atmosphere part. Here's the ocean part. It looks less noisy, it's more obviously just going up and down, whereas there's a lot more monthly jumping around because that's just how the atmosphere is. It's noisier than the ocean. So these are the two time series. You can see that there was a famous El Nino event in 1983, big spike in temperatures here, and a big negative SOI, and so on. So if you plot the two time series together, it's a bit hard to look at, but the blue line is the, let me get this right. The blue line is the ocean temperature and the red line is the Southern Oscillation Index. So this is this 1983 event, big spike in sea temperatures in the eastern tropical Pacific and a big negative value, but very weak trade winds that went along with that. Same story in 1997, that was another big event, and also in 2016. And because the ocean temperatures go up so much in the eastern Pacific, in an El Nino, that can actually boost global average temperatures. So we had relative spikes in global temperatures in these three events particularly. And a La Nina event where the temperatures in the ocean go down, that can also take a tenth of a degree off the global average temperature. Although El Nino events tend to be stronger than La Nina events, for reasons I'm not going to go into because I've already run out of time. So just to sort of wrap up here, here's some typical plots. This is from a blog post from the I've forgotten the name of the website, very well-known website that talks about climate stuff. It's in the notes. It's sort of a composite, but for an El Nino event, you can see this is a global plot. North America here, New Zealand here. Get this tongue of warm water that's centered right on the equator, and it sticks out to about the date line, but it's strongest in the eastern Pacific. So it's the sea temperatures here that I was showing in that time series before. And you get cooler water either side of that in the western Pacific, and so on. And then for La Nina, you've got almost the opposite case. You've got colder than normal water centered along the equator from about the date line to South America, and warmer than normal water in a so-called horseshoe in the western Pacific, either side of that. And looking at this PMEL site, this NOAA website in the US is really good. They've got a great set of pages. This What is El Nino? And this is just a time series showing how sea temperatures vary across the Pacific. This is centered on the equator, average from 2 south to 2 north, and Indonesia on this side and South America on this side. And you can just see, and this is time and years on the vertical scale, this waxing and waning of the temperature gradient. This is the total sea temperatures. This is the differences from normal, where you've got the cold water in the east, so La Nina event, where you've got the warm water, an El Nino event, and so on. So this sort of pulses backwards and forwards on a time scale of a year or so. And a paper there was a whole issue of the Journal of Geophysical Research in 1998 devoted to understanding of the El Nino cycle. This is just one plot from that, and it shows the depth of the 20-degree C isotherm, which is a proxy for how deep is the thermocline. And you can see, I haven't bothered with the colour scale as per usual. The darker colours are deeper, basically, and these arrows are the difference from normal and the average trade winds across the Pacific. So where the arrows are large, you've got a La Nina event, and you've got a deep thermocline in the west. Where they're small, you've got a shallow thermocline in the west and a deeper in the east, and so on and so forth. Sea temperatures difference from normal here, and rainfall. So the rainfall moves out into the central and eastern Pacific during an El Nino event when the trade winds become very weak. So anyway, yeah, there's a lot of cool information in this paper and many, many other papers. It's very well documented, this whole ENSO cycle these days. And yeah, here's another plot from that paper. In fact, these are the total amount, the sort of absolute quantities. These are the differences from normal. Yeah. So you can see in the Eastern Pacific, you're pulsing between cool conditions for a year or so, then warm conditions, then cool conditions, then it sort of goes to nothing for a while, etc. And associated with that, you can see these traveling waves of higher and lower 20 degree isotherm, higher and lower depths of the thermocline that move across the Pacific from the west to the east. These are these waves on the thermocline. And the rainfall patterns, the red colours are increased rainfall, I would have to say, going along with the SSTs. So when you've got warm seas in the east, you get more rainfall in the central and eastern Pacific, and so on. Okay, last slide. This is a schematic. Obviously, this is just a summary of how El Nino events affect weather, short-term climate over the globe. New Zealand doesn't feature here, but New Zealand is quite strongly affected because the winds, the westerly winds that dominate our climate, ramp up in an El Nino because you've got the negative SAM, and they decrease because of the positive SAM, you could say, in the summer in a La Nina. But anyway, that aside, you can see that the effects of El Nino they're not quite global, but they cover a good part of the globe. Most of Eurasia doesn't really feel anything, but I did a bit of research when I was on a sabbatical in the UK a couple of years ago, and there's actually a measurable effect on the strength of the North Atlantic storm track and the effect on the weather in Britain a year later, a year after an El Nino event. It's a long story, but some of the energy from that takes a while, it eventually propagates into the North Atlantic. So I would say, given enough time, El Nino and La Nina events pretty much affect the whole of the global climate, and that's what I was saying. It's the biggest signal in the climate system after the seasonal cycle. Okay, poof. Well, that was a lot of material. So let me just press the escape button and stop the share. And yeah, any thoughts in the remaining 13 minutes?
I've been madly writing notes. I think I'm going to have to go through and unpack it again before I make some resources for this.
Okay, and look, and I'm happy to respond by email and whatever over the course of the rest of the year or whenever you're working on this. I know it's quite a lot of stuff. I've at least mentioned most of the things I wanted to mention, but it's there's many research papers that go along with each of those things. So
No,
yeah.
it's been really great, James. I'll let everybody know that I've just put a link to a Google Drive folder that has the presentation in it. So you guys can access that. I think you've updated a few of the slides, James, so I can update
I have, and I updated the notes stuff, on the PowerPoint under the slides for each of them. There's not notes for everything because some of them is just text, but all of the figures I've got a bit of guff about what they mean and maybe a link to a paper that they came from, kind of thing. Brilliant. So hopefully useful.
James, I know you do a weather forecast quite regularly at Vic Uni. So can you give us a La Nina or an El Nino forecast for this year?
Oh, yeah, sure. And I could dial up the map and share it and all that, but I won't bother, I don't think. No anchovies on the shelves at the moment. Well, that's really interesting. That could be a delayed effect of the last El Nino. So at the moment, I was saying before that the tropical ocean in the Pacific is in a La Nina state. It's a pretty weak one. It's borderline neutral, but it's officially a La Nina state. The sea temperatures are below normal, but over 0.5 degree in the Eastern Pacific. But the atmosphere is struggling to respond. The trade winds have become a bit stronger just in the last couple of weeks, but there was nothing happening until then. So officially we're in a La Nina state, and the timescale of the it takes months for them to play out. So we're going to be in this weak La Nina state over the summer. And the outlook from NIWA, which is largely based on that fact, is saying, weaker westerlies, warmer conditions, we're getting more wind from the north, wet, in places exposed to the north, like Bay of Plenty, Northland, Auckland, Coromandel, etc., and maybe Nelson, and then dry in places that are sheltered from the north, such as Manawatu and Wellington and the west coast of the South Island. So if that plays out, and if we get the positive SAM that you would normally get in La Nina, it should be quite a sunny and warm summer, but possibly a wet summer in the northern half of the North Island. And that's what Niwa are saying, I think, when you look at their seasonal outlook. And I can't do any better than that, how it's actually going to play out. What the weather will be like on Christmas Day, your guess is as good as mine, as the song goes.
More importantly, am I going to see an aurora?
What's that, sorry?
Am I going to see an aurora tonight?
Oh, you wouldn't see it at my place. It's looking pretty cloudy out the window, so I'm not even going to try.
Yeah.
So
everybody knows, I've already started putting together like a student suitable PowerPoint resource, and that will be added to the slideshows on the Google Drive as well.
Cool.
I might get Jim and James to kind of proof and give some feedback on those, so that they'll definitely be there and ready for next year. So the ramp, the next year's exam will be based on the ramp standards. So if NZQA choose, there'll be a question on SAM and or ENSO in the atmospheres paper, and there won't be any ENSO in the oceans paper after this year. But that's kind of where we're at. Anybody else got any questions, or before we wrap it up?
I've just got one question for James. I just want to know, like, from your perspective at uni, what would you want an earth scientist from school to actually be capable of doing?
That's a great question. I think to understand the basic mechanism behind the ENSO cycle and the SAM oscillation, not the details of the physics, but just to understand that ENSO is based in the tropical Pacific, that it has a timescale of about a year, it involves the atmosphere and the ocean, and the SAM is a much noisier, faster beast that jumps up and down on a weekly basis, and it's all about the storms and the westerlies over the Southern Ocean. If students get that picture in their heads, I'd be pretty happy, because they can go on from there to understand the details at university or whatever comes next.
I think one thing I've really taken from our chats, James, and this webinar as well is the theme of the waves that kind of oscillate backwards and forwards in the atmosphere is a really good way to look at that I'll be kind of bringing that into my teaching. Absolutely. That's really good.
Yeah. And as I was preparing these slides, I was thinking, I could have quite a bit more on these Rossby waves and the Kelvin waves in the tropics. It's a whole, lecture or two I give in my climate dynamics course, and I thought, I haven't got time for this.
That's it. I had to look those words up when I first saw them.
Okay, very good. And
I saw it. I've seen a picture. The way I understood Rossby waves was actually from a northern hemisphere, and I try to keep well away from northern hemisphere, but it showed that the British Isle was completely covered in snow, and a Rossby wave had come down like that, so that all the cold Arctic air was funneling into Britain. And then another time it was having very high temperatures, and the Raspberry wave was going like that. And it seemed to go like that right around the top of the northern hemisphere. So is that similar to the southern?
That's the classic northern hemisphere Rossby wave story. But
I usually try very hard to avoid.
And it's the physics is the same in both hemispheres, but because of the difference in the distribution of land masses, the way it all plays out, it's very different. And there's been other great things for students to get. I mean, it's not exactly my lecture, my webinar, but it's an important feature of the globe, because of the distribution of continents is so different in the two hemispheres. You get very different average states of these Rossby waves and jet streams and all the rest of it.
All right. Well, I think we might wrap it up there, folks. Thanks very much, James, for giving us your time. It's been very generous, and I think that's really going to help us with our teaching next year on something that I don't think many of us are too familiar with. So.
Yeah, and it's great to think that I've had some kind of input into that. It's very cool.
Yeah, appreciate that. So I'll stop the recording now.
Okie doke.